In the last lecture, we discussed isomorphisms. Today, we are going to cover a wider class of transformations that are called linear transformations. So these include isomorphisms as special cases. So we begin with a discussion of what a function is. Right? So informally, a function f from a set A into set B, so from a set A to a set B, is a rule that assigns to each element A in the set A one element which is called f of A in the set B. Right. So if B is equal to f of A, then we call B the image of A, and A we call the pre-image of B, well, under F. And so sometimes we call A the domain of the function f, and B is sometimes called the codomain of f. Now, this is not a rigorous definition of a function, and of course there is a formal way to define a function, but this definition will not make you happy, and it's not practical. So we're not going to discuss the formal definition, and so it is just important that we understand how functions work informally. Having introduced the terminology involving functions, now we're ready to define a linear transformation. Let V and W be two vector spaces over the same field F. Definition. A function t from V into W is called a linear transformation if it satisfies two properties. One, for every V1 and V2 in the space V, we have T of V1 plus V2 is equal to T of V1 plus T of V2. And the second property, for all V in V and all scalars C in F, we have that T of C times V is equal to C times T of V. Now, what we see here is that there is a close similarity between the definition of a linear transformation and the definition of an isomorphism. So we have the same two properties, 1 and 2, and the only difference is that for isomorphisms, we have one more additional requirement, that an isomorphism has to be bijective. So we can say that an isomorphism is nothing but bijective linear transformation. Now, let us state some elementary properties of linear transformations. So the first property is that T of a zero vector is equal to zero vector. So any linear transformation must send zero vector into zero vector. And so to prove this, so just as we did it for isomorphisms, so set C equals 0 and V equals 0 in property 2, right? So if we do that, then we will easily derive that T of 0 is equal to 0. And so the second property is a way how to combine 1 and 2 together. And in fact, we can replace 1 and 2 with a single property. And this says the following, that if we apply a linear transformation to a linear combination of vectors, then this is equal to a linear combination of images. So C1 T of V1 plus CK T of VK. And we can derive this by applying first kind of compatibility of our linear transformation with addition, right? So by 1, so by property 1, so this is equal to T of C1 V1 plus dot 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 T of CK VK. And then by property 2, we can pull out the scalars out of each T, right? And we obtain then this equality. And so this means that a linear transformation transforms linear combinations into linear combinations. And so in fact, so we can replace, so 1 and 2 are special cases of this property. And so one can replace these two properties with a single but slightly more complicated property. Conceptually, a linear transformation is a function between two vector spaces that respects the operations of a vector space. So it transforms a sum into a sum, right? So note that here, so this addition is carried out in vector space V, whereas this addition is carried out in a vector space W. And it transforms constant multiples into constant multiples. And again, so here this constant multiple is taken in V, and this constant multiple is taken in the vector space W. Now let us look at some examples of linear transformations. So consider the following linear transformation from the space F2 in the space F, where T of AB is equal to A plus B. So here we have a rule that assigns to a two-component vector AB a scalar A plus B. So let us show that T is linear. So to prove this, we need to check two properties, that T of V1 plus V2 is equal to T of V1 plus T of V2. And the second property, that T of C times V is equal to C times T of V. Take two arbitrary vectors V1, and so here it's good to specify how this vector looks like. So we're going to write A1, B1, and V2, which is A2, B2, in F2. Right? So we're going to check that for arbitrary vectors, this property holds. And to check this property, again, we compute the left-hand side, the right-hand side, and verify that they are the same. So now the left-hand side. So we have T of V1 plus V2. So here we add these two vectors, A1, B1 plus A2, B2. Now, if we add these two vectors and we add vectors component-wise in vector space F2, so then we get the vector A1 plus A2, B1 plus B2. Now, here we use the rule that defines our transformation. So our transformation transforms a two-component vector into a scalar, which is the sum of the two components. So the result will be A1 plus A2 plus B1 plus B2. Now, let's compute the right-hand side. So the right-hand side is T of V1 plus T of V2. Now, this is going to be T of A1, B1 plus T of A2, B2. And T of A1, B1 is going to be A1 plus B1. And T of A2, B2 is A2 plus B2. And because addition in a field is commutative and associative, so we have the equality here. So this sum is equal to this sum. And what we see is that the left-hand side is equal to the right-hand side, and so the first property holds. And the second property I leave for you to check as an exercise. Next, let us consider some linear transformations of geometric origin. So here we're going to look at linear transformations from R2 to R2. So the first example will be dilation. So here, this transformation will take a vector and multiply it, say, by scalar 3. So here, every vector is dilated by a factor of 3. So this is kind of expansion transformation of a plane. Now, let's verify that this transformation is linear. So we need to check that for all V1 and V2 in R2, we have T of V1 plus V2 is equal to T of V1 plus T of V2. So now to prove this, we say, so let V1 and V2 be two arbitrary vectors in R2. Then, so the left-hand side, T of V1 plus V2 is equal to 3 times V1 plus V2. And now we use the distributive law in vector spaces. So this is equal to 3 times V1 plus 3 times V2. And the right-hand side So T of V1 plus T of V2 is, by definition, is equal to 3V1 plus 3 times V2. And we see that left-hand side is equal to the right-hand side. So the first property holds. Right? And for the second property, so we need to check that for all V in R2 and for all scalars C in real numbers, we have that T of C times V is equal to C times T of V. And now we look at left-hand side. So T of C times V is equal to 3 times C times V. And the right-hand side, C times T of V, is equal to C times 3 times V. But by axioms of vector spaces, so this is equal to 3 times C times V, where this multiplication is carried out in real numbers. And this is equal to C times 3 times V. So since real numbers is a field and multiplication in a field is commutative, so what we have is that the right-hand side and the left-hand side are the same. And now this gives us the proof of the second property of the linear transformation. So it's clear that here we can replace this constant 3 with any other constant. So for example, 2 or 5, right? Or we can consider a transformation, so T of V, which is 1/3 times V, right? So this will be a contraction. Or we can consider T of V, which is equal to minus V, right? So this flips each vector, so this is sometimes called central symmetry transformation. So two other special cases of these constructions are zero transformation. So this is when T of V goes to 0 vector for all vectors V, right? So this, so here we choose multiplication by scale 0, for example. And the proof will become exactly the same, that this transformation is linear. And identity transformation. So where T of V is defined as V, right? So this transformation, it's a very lazy transformation. So it sends every vector to itself. And so one can view this as a special case of this if we choose the multiplier to be equal to 1. And again, by the same proof, we can show that each of these transformations is linear. So the next transformation that we want to consider is a reflection. So this, say, in x-axis. So this can be defined geometrically, right? So if we have some vector v, then to find its image, so we perform a mirror reflection here in x-axis, and so this vector is going to be t of v. So we can see the mirror reflection of v when we view x-axis as the mirror. And so now one can prove geometrically that this transformation is linear. Now, what is the first property? So the first property says that T of u plus v is equal to T of u plus T of v. Now, let's make a picture. So here we have our mirror, and suppose we have two vectors. So we have a vector u, and we have a vector v. Now, in the left-hand side, we have their sum. So this means that we need to take a parallelogram. And so this vector here is u plus v. And to compute the left-hand side, we need to take u plus v and reflect it. Right, so now we take a reflection. And so let's actually reflect each vector. So if we reflect here, so we get T of u. And if we reflect this vector, then we got here T of v. And so our claim now is that so T of u plus v is equal to T of u plus T of v. So in this picture, we have two parallelograms. So this is the first parallelogram, and here is the second parallelogram. And these two parallelograms are mirror images of each other with respect to x-axis. Since a reflection of a parallelogram is again a parallelogram, so what we get is that the sum of T of u and T of v will be the diagonal of this reflected parallelogram. So this means that this vector here is T of u plus T of v. Right? So because addition of T of u plus T of v is obtained through parallelogram rule. And because this parallelogram is a reflection of the parallelogram on the top, so we get that this vector here is also the image of u plus v. And so the same vector is equal to T of u plus v. And because of the geometric properties of this symmetry, we have that this reflection transformation transforms the sum of two vectors into the sum of their images. So the same can be done for scalar multiples, right? So here we need to check that T of c times v is equal to c times T of v. So if we have a vector and we take its scalar multiple, so this is v and this is c times v, then if we reflect both vectors, then here we get T of v, and here we get T of c times v. Right, so these are mirror reflections. And what we see from this picture is that T of c times v is the vector T of v rescaled, so it's equal to c times T of v. So from the geometric properties here, we see that this transformation is linear. Another important class of transformations of a plane is rotation in some fixed angle phi. Right. So what we have is, say we take a vector u, and so we rotate this vector in angle phi, and we get T of u. So now, what we need to verify is the following two properties, that T of u plus v is equal to T of u plus T of v. Now, how do we verify this? So we take two vectors, u and we take another vector v. And again, u plus v is obtained using the parallelogram rule. Right, so this vector here is the vector u plus v. Now, let's take this parallelogram and let's rotate it by angle phi. So we know that rotations preserve the shape of our figure. And so because of this, when we rotate the parallelogram, then the image of it is going to be, again, a parallelogram. Right, so what we have is, so this is our vector v here, and so the rotated parallelogram will be like this. So here, okay, so this is t of v, right? And then this diagonal is going to be t of u plus t of v. And so because when we rotate this parallelogram, we get this parallelogram. So this tells us that the image of u plus v is equal to t of u plus t of v. And we see that this property holds. And in a similar way, one can show that t of c times v is equal to c times t of v. So this says the following. So if we take a vector and rescale it and then rotate, the result will be the same as if we take a vector, first rotate it and then rescale. And so these two properties together demonstrate that rotation is a linear transformation. Another example of a linear transformation on a plane is a projection. Or, so more specifically, let's take orthogonal projection to line, say, y is equal to x. So how does this transformation works? So here we have a plane, and let's consider a line y is equal to x. So to compute images of vectors, so we take any vector u, and what we do is we drop a perpendicular from the endpoint of u to the line y is equal to x. And so then this vector on this line is going to be the image of u, right? So this will be t of u. And so in this way, so the whole plane will collapse to the line y equals x, right? So all images of all vectors will only live on this line. And so again, it's easy to use geometry to see that the projection, this orthogonal projection transformation, will satisfy the two conditions of a linear transformation. Our next pair of examples will have the flavor of calculus. So let's consider differentiation transformation. So in this case, our transformation will be defined on the space of polynomials with values, again, in the vector space of polynomials. And the rule for this transformation is, so t of a polynomial p is going to be the derivative of this polynomial p prime. So for example, so t of x cubed plus 2x squared plus 5x plus 3 is equal to the derivative of this. So it's going to be 3x squared plus 4x plus 5. Now, so let us show that differentiation is a linear transformation. So for this, we need to verify two properties. The first one is T of P plus Q is equal to T of P plus T of Q. And the second property, that T of C times P is equal to C times T of P. Now, our transformation is differentiation. So let us translate this abstract property into more specific situation here. So what we have is that one will say that the derivative of P plus Q is equal to the sum of the derivatives. And the second will say that the derivative of C times a polynomial is C times the derivative. But these are two well-known theorems from calculus. So this is the sum rule for the derivative. So the derivative of a sum of two functions is the sum of two derivatives. And the second rule is the constant multiple rule. So if we multiply a function by a constant and take the derivative, it's the same as to take the derivative and multiply by the same constant. So these are well-known theorems from calculus or from analysis. And since we know these theorems, so these theorems say that differentiation is a linear transformation. For our next example, let's take integration. So let's take a transformation S from R of X, from the space of polynomials, into the space of polynomials, where S of a polynomial P is defined as the integral from 0 to x of P of t dt. So here I assume that you are familiar with integration, and so if not, just disregard this example. And so basically here we take the antiderivative of a polynomial with a zero constant term. So this means that S of x cubed plus 2x squared plus 5x plus 3 is going to be equal to 1/4 of x to the power 4 plus 2/3 of x cubed plus 5/2 x squared plus 3x. So this is the antiderivative transformation. And again, so we can check that it's linear. So that S of P plus Q is equal to S of P plus S of Q. And S of constant times P is constant times S of P. And again, these are two theorems from calculus. So the first one says that the integral of P of t plus Q of t dt is equal to the sum of two integrals. And the second property says that the integral of a constant multiple is the constant multiple of the integral. So these two theorems from calculus tell us that integration is a linear transformation. Our final example of a linear transformation will be closer to linear algebra. So let us talk about transpose of a matrix. So here we give a definition. So the transpose of an M by N matrix A. So let's, as usual, write A as follows. So A11, A12 up to A1N, A21, A22 up to A2N, and so on. AM1, AM2 up to AMN. So the transpose of this matrix is defined as a N by M matrix denoted AT, so the transpose of A. And where what we do is we write rows of A as columns of the transpose. So here we're going to write A11, A12 up to A1N. So A21, A22 all the way up to A2N, and so on. AM1, AM2 all the way up to AMN. And let's give an example. So if we take the matrix 1, 2, 3, 4, 5, 6, then its transpose is going to be a 3 by 2 matrix, where we write the rows as columns. 1, 2, 3, 4, 5, 6. So this is a very simple operation on matrices. Now we recall that matrices of a fixed size form a vector space where we add vectors or matrices component-wise. And now we can say that transpose becomes a map or a function T from the space of matrices of size Mn over a field F to the space of matrices of size N by M over the field F. And what we claim is that this transpose is a linear transformation. On the spaces of matrices. So to prove this, we need to check the following two properties. That the sum of two matrices is transposed into the sum of transposes. And the second property is that if we multiply a matrix by a scalar, then the transpose of this is equal to k times the transpose of matrix A. I'm going to prove the first property for the specific size, let's take 2 by 3 matrices over the field F, right? And so let's consider the transformation of 2 by 3 matrices into 3 by 2 matrices. And the general case is exactly the same. So, all right, so let's take matrix A to be the matrix A1, B1, C1, D1, E1, F1, and the matrix B to be A2, B2, C2, D2, E2, F2. And now we calculate the left-hand side and the right-hand side. So in the left-hand side, we have two matrices A1, B1, C1, D1, E1, F1, plus the matrix A2, B2, C2, D2, E2, F2. So we take the sum and we take the transpose of the result. So the sum of these two matrices is going to be A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2, E1 plus E2, F1 plus F2, and then we take the transpose of this whole thing. And the result is going to be a 3x2 matrix. So we have A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2, E1 plus E2, and F1 plus F2. Right? So this is the result of the calculation of the left-hand side. And for the right-hand side, we have A transpose plus B transpose is equal to the sum of the following two matrices. So we take the transpose of this matrix. So that becomes A1, B1, C1, D1, E1, F1, plus the transpose of the second matrix, A2, B2, C2, D2, E2, F2. And the sum of these two matrices is obtained component-wise. So we get A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2, E1 plus E2, F1 plus F2. And what we see is that right-hand side is equal to the left-hand side. So this means that this property holds. And again, this property I leave for you as an exercise. Verifying these two properties will prove that transpose of a matrix is a linear transformation.